Well, welcome to the starting point, the discussion for the solutions to the questions at the end of Chapter 12, which are on solid-solid mixing in Fundamentals of Particle Technology. And from the diagram in front of me, you will see that we kick off by talking about two important aspects. The first one being specification, which is a value. So we might say a value of some value, let's say 0.1, where 0.1 by mass fraction is 10%. So it could be 10% of a product that we're talking about as our specification. And that specification could have a tolerance on it. So we could say plus or minus a certain percentage around that 0.1 value. And then we have the confidence in achieving what the specification says. So let's persist with our value of 0.1. And if we say that we want a pharmaceutical active ingredient, say, to be equal to 10% by weight in a powder product, and this could be in a sachet or a packet or even a pill, but we'll stick with a packet or sachet first. So that's obviously 10% active ingredient, 90% is the rest, and the rest will be the bulking agents, disintegrants, whatever else. Okay, so this is what our specification is, the 10% by weight active ingredient here. And we would, if we were to take samples of lots of different packets, we'd get values of the active ingredient that we would expect to be following something like a normal distribution. So some of the packets would contain more than 10%, some of the packets could contain less than 10% of the active ingredient, but we would expect them to be distributed around the 10% value. Now, if we have a specification that is plus or minus, then we might even have a specification that looks something like that we have 10% plus or minus some value that gives us a range. And then when it comes to a confidence, are we going to be within that range? So the classic confidence intervals that are used in statistics are something like 95%, it's not quite 95%, but we'll call it 95%, is plus or minus 2 times the standard deviation. So if we take lots of samples, lots of packets, open them up and find out there's 10%, we can work out what the standard deviation of the active ingredient is. The next statistic, which is quite memorable, is the 99.8% statistic, which is plus or minus, roughly speaking, 3 times the standard deviation. So we would expect 95% to be within 2 times the standard deviation around the mean value, and we would expect 99.8% to be 3 times, plus or minus 3 times the standard deviation around the middle. So if we're doing mixing of a free-flowing powder and we're having to mix this powdered product which has 10% active ingredient, then we're going to hope for each one of our products, our sachets, having this plus or minus 2 or 3 times around the mean value, 2 or 3 times by the standard deviation. And if, say, we're happy with, let's have the 99.8% confidence limits, then we know we're going to end up with one sachet down here, so that's one packet with a value higher than that 3 times the standard deviation, and we know we'll have one packet down here when considering 1,000. So that's out of 1,000 packets, because 99.8 means we've got 998 inside that specification, but we know we're going to have one up here and one down here. Okay, now if that was a pill that we had and we were talking about active ingredients around a pill, then we could be in danger, because we could be in danger of overdosing somebody by having one pill in 1,000 giving a high value. Then you might need to go to something that's more like 99.99 blah blah percent, which of course will be some other value of times by the standard deviation, but that will give us one pill, not in 1,000, but per 10 to the lots that will be possible. So we'll have a confidence there that we won't be poisoning people, other than that unlucky person who gets that one pill in a lots, and of course we want to make that a big lot. So okay, so here are our confidence then related to the standard deviation, related to the normal distribution. So can we actually predict what we are expecting from the powder properties? Well, we can. There's quite a famous equation which comes from the work of Lacey and then Stanger and then Poole, Taylor and Wall. And it's an equation which we can use to predict the standard deviation. The equation is written in terms of the variance rather than the standard deviation, and I've put the R in there to say that this is a random mixture. So a random mixture of a binary component powder with a certain proportion P of one component and Q of another component, and then I'll put M in here and define it in a moment. Then the variance is expected to be this, where WP is the average mass of one component, the P component, and we times by the weight proportion, we times by the weight proportion of the other one, the Q, plus the the average mass of the particle Q times by the weight proportion P. So it's a fairly straightforward equation, fairly simple equation. So I say P and Q are the weight proportions of the binary mixture, so we're expecting them to add up to 1. Okay, WP is the mass of a particle if we assume the particle is spherical, so it doesn't have to be, but so long as we know what the shape factor is, we can apply that, and then we need to know what the density is and multiply by the average particle size. Okay, and likewise WQ is a similar, it's the average particle size of the other component times by its density, again cubed. So if we call that component P and that component Q. Okay, so these are masses. This will be in grams. Okay, now finally M is the mass of the sample and or product. Mass of sample and or product, and that is this thing called scale of scrutiny. Scale of scrutiny. Okay, so how does that work? Well, if that is mass, we'd expect that to be in terms of grams. We know we've got this in terms of grams, we've got this in terms of grams. They all cancel out in terms of its units, and therefore we're getting the variance, which we can take the square root of to get the standard deviation, to do an analysis similar to what I just spoke about a few moments ago. But let's just finish off by talking about the scale of scrutiny how big a mass of sample should we take from a mixture? Well, that's an easy one, because the mass of sample we should take from a mixture is exactly the same mass as what the product is. So if we have, let's say, sachets of 50 grams as a product, so coming back to our sachets just here, if the sachets are 50 grams, then the mass of a sample should also be 50 grams. So each one of these samples should be 50 grams taken from the industrial mixed powder in terms of deciding whether it's been mixed for long enough time, for example. And if you take a 50 gram sample and you take, let's say, 10 times 50 gram samples, then that will give us enough data to calculate the mean value, and also we can get the standard deviation, and we would expect that standard deviation to be what we're predicting from this equation here, or the square root of this equation here, according to Poole, Taylor and Wall. So that's the expected variance, or the expected standard deviation, when we have achieved random mixing of our powder for a free-flowing powder. Now clearly what we have here is a binary model, binary meaning two. So we have two components, the components P and Q. Most pharmaceutical products have multiple components, not just two, but that's okay, not a problem, because all we will do is we'll say that P, for example, is our active ingredient, and Q is all else. So we just combine all the flow aid, so that's all else, sorry. So we'll combine all the flow aids, the disintegrants, the binders, whatever else that we've put into the system, into a average of Q, and just focus in on the important thing, which is the active ingredient, and look for the standard deviation of the active ingredient for use in our confidence discussion in terms of what we're expecting around the mean. And perhaps the best example of how we can do this is question 2. So question 2 is very much this sort of consideration of the specification, the confidence in achieving it, and what the expected variation around the mean value is. So a good example to see how this works is to now look at the calculation question 2. Okay, thank you.